everyone, good day. Today we shall be looking at further examples on circular motion. As you can see, question 1, we have the first question here is, I think it came out this May, June. I've solved this question before in one of my videos, but let's see how it goes. Now we have a steel sphere of mass 0.2 kg. The mass of this sphere is 0.2 kg. So the weight of the sphere is W equal to mg. That's 0.29 g. That's the weight of the sphere. It's suspended in equilibrium. The mass is held in equilibrium in a vertical spring. The center of the sphere is 8.5 centimeters from the top of the springs. This is like the original length. The original length of the spring. The original length is 8.5 centimeters. So now remember that it's suspended in equilibrium. So there is always a tension in the spring. It's always acting outside. Look at the direction. It's always acting outside. Since the system is in equilibrium, it means that the tension is equal to the weight. So resultant force in this case is tension minus weight. So since tension is equal to the weight, so resultant force in this case is 0. So there is no resultant force in this case. Now let's move to the next diagram. In the next diagram, the sphere is now set into motion. It is set into motion with a force. It's set into motion so that it is moving in a horizontal circle at constant speed. Horizontal circle at constant speed, which means suppose when you see constant speed, think about circular motion. Circular motion is the only motion in physics that an object is moving a circular path with a constant speed and the body is still accelerating. It's accelerating due to continuous change in direction. If you check my previous video, I explained this there. Now the question asks us, when you see, now let's analyze it now. This body has been displaced. Check the length. The length has increased from initial 8.5, look at 8.5, to 10.8, which means there is a force now. Force is the only thing that can bring out the extension. There is a force. In this case, in the first case, there is no force, no extension. Now there is a force. Force has been applied. There is an extension. So now the question asks us, the distance of the sphere blah is now 10.8 centimeters. I explain with reference to the forces acting on the sphere, while the length of the spring in figure 2.2, in the second figure, in this figure we are dealing with, the question asks us why the length is greater than the first figure. Now let's check the number of marks, 3 marks, that should be 3 points. Now let's analyze this diagram. Let me change the color so we can see the analysis. So from here, let's see the second. Let's analyze this one. This angle here with 27-degree vertical opposite angle. Now look at the position of the mass now. The mass is there. The weight is now here. Remember, the weight is still mg. Now, so in this case, the tension in this case has been displaced at an angle of 27 degrees. Let's resolve the tension vertically. This is the vertical direction of the new tension now. it has been moved sideways, X. Look at it here. Look at its position here and look at it. It has moved sideways, X, and vertically it has been displaced too. So let's resolve it. So somehow the free body diagram look like this. This is the tension. It has moved toward this side. I don't know the value, and this is the value of Y. Here is 27. Here is the tension now. It's like it. Now let's get the value of Y and X. Sine 27 is opposite over hypotenuse. So the value of X in this case is T sine 27. Let's get the value of Y. The value of Y in this case, adjacent over hypotenuse, is cos 27. The value of Y in this case is T cos 27. So the vertical displacement in this case, the vertical displacement Y is T cos 27, which is also the same thing. They are parallel to this point. So T cos 27, they are parallel. X is T sine 27, as you can see. Now in this case now in this new position, there are like two forces acting on the mass in this position. There is one force, T cos 27. There is another one toward the center. This one is upward. This one is T sine 27. There are two forces acting on it. Let's find the resultant force. Now it has a resultant force. Let's find the resultant force. There are two forces acting on the sphere, perpendicular to each other. But now the resultant force in this case, Pythagoras theorem, will be T squared sine squared 27 plus T squared cos squared 27. So resultant force in this case, T squared is common. Sine squared 27 from your maths plus cos squared 27 will give us 1. Like sine squared theta plus cos squared theta is equal to 1. So the resultant force is T squared. Now we have a resultant force. There's a resultant force. The value of the resultant force is T. Unlike the first one, the resultant force is 0. The first one resultant force is 0. The second one, we have the value of resultant force. So which means that there's a resultant force in the new position. That's the reason why it moved towards the right, and that's the reason why there is an extension. So what we're going to do now is that we now put that into writing. Now the first point is this. The first point will be T cos 27 T cos 27 T cos 27 and T cos 27 and T sine 27. That's horizontal force and vertical force act on the mass. Act on the mass perpendicularly. Act on the mass perpendicularly to give a resultant force equal to tension. That's the first point. That should be 1 mark. Another point is that the force, if you see the body, it moves sideways. It's moved toward the side. Look at it there. Initially it was here. Now it has moved toward the right. So there's a force that sets the body like that. So we can also say that, let's see, that's one point. And T sine 27, which is horizontal force, pushes the sphere to the what? To the right. So T sine 27 horizontal force pushes the sphere to the right to give, which provide, let me put like that, to the right. We need to analyze it properly. Pushes the sphere to the right, which provide the centripetal acceleration. The force is T sine 27. Is the one that provides the centripetal acceleration. So when it pushes the force to the right, it now starts accelerating around the circle toward the center. So this T sine 27 provides the centripetal acceleration. Hence, the tension in figure 2.2 is greater, we conclude, than the tension in figure 2.1. That is what they're asking. This, you get your full mark here. Figure 2.2. This is figure 2.1. Yes, you're correct. Let's move to the next one. The second question, B. The angle between the linear axis on the spring and the vertical is 27. You know that. Show that the radius R of the circle is 4.9. Let's go back to the diagram. Look at the diagram. So let me use another color so we could see it clearly. Okay, I can clean the diagram now. So because we use the first diagram, okay, I don't need to clean it. Let me just use another color. Okay, let me do this. Okay, this will work. Now from here to here is the radius, as you can see. From here to here is the radius. So from here to here is the radius, as you can see. Now the question asks us to show that the radius of the circle is 4.9 centimeter. So you can see it look like a triangle. From here to here is the radius, and this is 27. This is 27. What else again are we given? Well, we are given the length of this side, 10.8, as you can see there. So we are dealing with in meter. So we are going to use all the value of meter. 10.8, this centimeter. So you have to look for the radius R. Your SOHCAHTOA. Sine 27 equal opposite your R over hypotenuse. 10.8. When you cross multiply, so your radius is 10.8 sine 27. Let's punch it in our calculator. 10.8 sine 27 and we give 4.9 centimeter. We don't need to convert it to meter. The proof asks us to leave it in centimeter. Now the next question, show that the tension in the spring is 3.2. The tension in the spring is 3.2. Okay. Now, to find the tension in the spring, since the question show that the tension in the spring is 3.2, this upward force will be equal to this downward force. The upward force will be equal to downward force because so T cos 27 will equal to the weight. So T cos 27, what's the weight? The weight is mg. M is 0.9, G is 9.81. So T is 0.29 times 9.81 all over cos 27. When you punch it in a calculator, it's going to give us 3.19, which is approximately equal to 3.2 Newton. Next question. The spring obey Hooke's law. Now, very important. Hooke's law is force is proportional to extension. So now what's the force? What's the extension? Extension is always new length minus original length. Now, what's the cause of the extension? If there's an extension, it means there will be change in force. So the formula will be change in force equal to K multiplied by extension. Now, initially, the new force, in this case, you are dealing with tension because you are dealing with spring. Change in tension equal to this. So the first tension, remember in the first case, look at the tension. This one is in equilibrium. The tension is equal to weight. So the first tension is 0.9 G. And the new tension, when it's displaced in motion, what's our new tension? Our new tension is 3.2 Newton. So the change in force is 3.2 minus the weight, 0.29 times 9.81. That's the change in tension. This change in tension causes extension. What's extension? New length is 10.8. Original length, the first one, is 8.5. Remember, they are in centimeter. And the answer asks us to leave in the centimeter. So from here, so 3.2 minus first 0.29 times 9.81. That's 2.8449 minus 3.2. So that gives us this gives us 0.3551 equal to K. 10.8 minus 8.5. That gives us 2.3. So make K the subject of the formula. 0.3551 divided by 2.3. That gives us 0.15. So the spring constant is 0.15 Newton per centimeter. I hope it's clear. Now the next one. Next question. Now use information in B to determine the centripetal acceleration of the sphere. Remember the horizontal force. The horizontal force T sine 27 is the cause of is one that provides centripetal force. So we are looking for the centripetal acceleration. So from here, T sine 27, centripetal force is mass times centripetal acceleration. So centripetal acceleration AC is T sine 27 divided by the mass. So remember, in this case, the tension in this case is 3.2 sine 27 divided by mass. Mass is 0.29, not weight. So when you punch this into calculator, 3.2 sine 27 divided by 4.29 we have 4.99, which is approximately 5 meters per second square. That's our centripetal acceleration. The next question, calculate the period of the circular motion. Now, which formula relates period? Okay. Now, in CIE questions, the question is always linked. There's a reason why they ask us this C question is also link it to this next question. The fact that they ask us to find centripetal acceleration, there might be a relationship. Centripetal acceleration is centripetal acceleration, remember, is v squared over r, and where v is r w, so that will be r squared w squared over r. So centripetal acceleration can be r w squared. So if centripetal acceleration is r w squared, so centripetal acceleration is r. What's the formula for angular velocity? It can be 2 pi f or 2 pi over t. I need t in this case. Don't forget to put square. At the end of the day, centripetal acceleration is r times 4 pi squared over t squared. We are looking for period. Make period the subject of the formula. That will be r 4 pi squared all over centripetal acceleration. So at the end of the day, our period in this case is square root of r 4 pi squared over centripetal acceleration. So the period will be square root of, what's the radius? I think we got our radius as 4.9 centimeter in the first part. What they asked us to prove, the radius 4.9 centimeter. So in this case, convert the unit is the proper unit seconds. So make sure that all your variables all your quantity are in the right SI unit. Radius is 4.9 centimeter. That's 4.9 times 10 to the power minus 2. Multiplied by 4. Pi is 3.14. Remember, there's a square on top of it. So all over centripetal acceleration is 4.99. At the end of the day, punch this in calculator. You're going to have 0.628, which can be 0.63 seconds. That's the end of the first question. Now let's see the second question, second example. State what is meant by centripetal acceleration. Now, if you are following my my channel, I did a previous video explaining centripetal acceleration. Now, let me quickly explain it. Now, a body in circular motion, any body in circular motion, the direction of the particle. Now, let's assume this is a particle. The direction of the particle, for the body to be in circular path, the direction of the particle or velocity of the particle must be tangential to the circle. Must be tangential to the circle. Must be tangential to the circle for that body. So this is the velocity v1, v2, v3. For the body to be in circular path, the direction must be tangential. I remember that in circular motion, the acceleration is always directed. The acceleration of the particle is always directed toward the center. So which is the radius? In maths, radius and tangent, they're always perpendicular toward each other. Radius and tangent are always perpendicular to each other. So we can say what is meant by centripetal acceleration is an acceleration which is perpendicular, acceleration which is perpendicular to the direction of velocity, or acceleration which is perpendicular to the velocity. Let's put it down. Acceleration which is perpendicular to the velocity of the acceleration which is perpendicular to the velocity of the object in a circular path. You need to be very careful. You need to be clear at the same time. Acceleration which is perpendicular. Centripetal acceleration is an acceleration which is perpendicular to the velocity of the object in a circular path. That's it. Now the next part. An unpowered toy car moves freely along a smooth track. Is initially horizontal. The track contains a vertical circular loop. Around the loop which the car travels as shown. The mass of the car is 230 grams as seen. The diameter is 62 centimeters. Assume that the resistive forces acting on the car are negligible. Still, what happened to the magnitude of centripetal acceleration of the car as they move from x to y? As they move from x to y, okay, we need to use different color. As they move from x, the car is moving from x to y. So it's going to cover a full diameter from x to y. Now, from x at this point, at x is at the low level, we can say potential energy is 0. At y is at the high level, it has gained height of 0.62. Diameter is 0.62, half of the circle. So that's 62 centimeters is 0.62. Sorry, I've already converted to meter in my head. So we can say potential energy is maximum due to the height in this case is the diameter. The potential energy at y is maximum because it has gained height of 0.62 meter. I remember that where the potential energy is 0, kinetic energy, at equilibrium toward the earth on the ground level, kinetic energy is maximum. Now, as they move from x to y, potential energy increases while kinetic energy decreases. So kinetic energy is 0 at this point, at point 1. So since kinetic energy decreases, I remember that kinetic energy is a function of velocity, half mv squared. I remember that centripetal acceleration is mv squared over r. So in this case, it's like a linear movement, in terms of gaining the height. In this case, since velocity decreases, and velocity is also a function of acceleration, centripetal acceleration. Since velocity decreases from x to y, acceleration also decreases. So the question asks us to state what happened to the magnitude of centripetal acceleration as the car moves around from x to y. It decreases. That's the answer. If the ask is reason, because kinetic energy decreases. And once kinetic energy decreases, the acceleration also decreases. Whatever acceleration involved also decreases. That's the simple truth. The second one, explaining the car remain in contact with the track. Why the centripetal acceleration of the car at point y must be greater than 9.82 Mach. Okay, now let's go back to diagram. I need to clean this. I hope you've recorded it. Let's go back to this diagram. Let's go back. Now, the question says explain if the car remain in contact with the track, why the centripetal acceleration of the car at point y must be greater. At point y, the car is there at point y. The car is there at point y. Look at the car. The weight of the car, is in this direction. And also, um, the reaction of the track on the car. The reaction of the track on the car is also downward. And another thing again, centripetal acceleration is also downward. Now, at this point, the reaction is downward. The reaction exerted by the track on the car is downward. The weight is downward. The question asks us, if the car remained in contact with the track, why the centripetal acceleration of the car must be greater than 9.8? So in this case, let's analyze it. In Cartesian, down is negative, up is positive. Both the reaction and the weight are down, negative direction. So we can say minus reaction minus weight. The answer will give us a negative answer. In this case, it's a negative centripetal force because it's toward the center. Everything, the resultant must give you centripetal force. When you multiply 2 by minus, we have reaction plus weight equal to centripetal force. Now, the question said, why the centripetal acceleration must be greater than 9.8. So in this case, centripetal force is the summation of the reaction plus weight. Weight is mg, right? Weight is mg. Centripetal acceleration. Okay. Now, centripetal acceleration in this case will be so now in this case, to get the centripetal acceleration, you need the normal reaction plus 9.8 mass. When we add the normal reaction plus 9.8 mass, it will give you centripetal force. Remember that whatever is the normal reaction, let's assume the normal reaction is 2. Let me give you, say, 1 plus, let me say the mass is 2. At the end of the day, 9.8 times 2, I think it's 19.6 or so. 9.8 times 2 is 19.6. 19.6 plus 1, 19.6 plus 1, it gives us 20.6. Now, can you see it? Whatever the value of mass or normal reaction, at the end of the day, it is centripetal force not greater than 9.8? Yes. Centripetal force is greater than 9.8 because the normal reaction has a value. Because the normal reaction is a variable that is added to 9.8 mass to give a value of centripetal force. So for my analysis here, our centripetal force is greater than mg, the weight, with the help of normal reaction. If there is no normal reaction, centripetal force is most likely equal to the weight, or the weight is most likely to be greater than centripetal force. Now, the only way centripetal force is greater than the weight is the help of normal reaction. You can see it. So, for centripetal force to be greater than weight, it requires the normal reaction. Now, centripetal force is mass times centripetal acceleration. Weight is mg. So mass cancel mass. So if centripetal force is greater than weight, automatically centripetal acceleration is greater than weight. So for this to happen, or for this to occur, they require the help of the normal reaction to have a value, or else the mass will skid off the track. So let's put it like this. Let's put it down. So the first one, we have 2 marks. So centripetal force, centripetal force, centripetal force must be greater, than the weight of the car, than the weight of the car. As analyzed earlier, centripetal acceleration 2. Once centripetal force is greater than the weight of the car, centripetal acceleration will be greater than g, as shown earlier, with the help of normal reaction. So how will I put that? Centripetal force is greater than the weight of the car, which require the car, to be in contact, with the track. To be in contact means that there will be normal reaction. That's it. Contact force, normal reaction. I think that's what is needed. Now this third question, the initial speed of the car in B moves along the track 3.8 meters per second. Determine whether the car is in contact with the track at point Y. Remember that for the car to be in contact, centripetal force must be greater than weight, or centripetal acceleration must be greater than g, which means we need to get either the centripetal acceleration or centripetal force. Let's do that. So the initial speed of the car along the track is 3.8. Okay, let's go back to our diagram. So I need to clean this up again. I believe it's clear. Now, so the initial speed of the car, according to the question, is 3.8, and the initial speed is at x. The initial speed at x. So there's a speed at x. Remember I said potential energy at this point is 0. So kinetic energy is half mv. The speed here is 3.8 squared. Now, at this point at y, this at x, potential energy at y, it has gained height, is mg. Height at y is 0.62. That's the height at y. That's diameter. That's 0.62. Why the question said, oh, in this case, they said determine whether the car is in contact with point Y, which means the question assumed to be a speed at Y. So there will be kinetic energy at Y, but it will be lesser compared to this one. So kinetic energy at Y is half m speed at Y, because it's required to get centripetal acceleration. From the principle of conservation of energy, kinetic energy, total energy at x must be equal to total energy at y if resistive force is negligible, and the question initially said resistive forces are negligible. Total energy at y is equal to total energy at x. What is total energy at x? Potential at x plus kinetic at x must be equal to potential at y plus kinetic at y. That's principle of conservation of energy, POCOD. Potential at x is 0. Kinetic at s is half m. Speed at x 3.8 squared. Potential at y, this is equal to potential at y is mgh, which I shown earlier, and h there is 0.62. Kinetic at y is half m. Speed at y. So you can divide through by m. When you divide through by m, I think we have half times 3.8 squared equal to g is 9.81 times 0.62 plus half vy squared. So now let's make use of our calculator. 3.8 squared times 0.5. This one gives us 7.22. The other one 9.81 multiplied by 0.62. This gives us 6.0822 plus half vy squared. So this goes like this. So minus 7.22, it gives us 1.1378 equal to half vy squared. At the end of the day, vy squared will be 2 times 1.1378 multiplied by 2. So we have, so vy, the square root of 2 times 1.1378, that's 2.2756. For the square root of 2.2756, 2.2756, the square root gives us 1.5. Oh, sorry. So the speed at y is equal to 1.5 meter per second. So if the speed at y is 1.5 meter per second, but what we're looking for, is the question asks us that determine whether the car is in contact with the track at point y. Like the condition, from the condition for the car to be in contact with the point y, centripetal force must be greater than the weight, or centripetal acceleration must be greater than g. And what is centripetal acceleration at y? V square y over radius. That's 1.5 squared. The radius is 0.32 because the diameter is 0.31 because the diameter is 0.62. Half of it is radius. So 1.5 square. 1.5 square divided by 0.31 will give us 7.3 meter per second square. This is the acceleration. So now from this, the acceleration, centripetal acceleration, from here, centripetal acceleration is 7.3, which is less than g, 9.81. So which means that determine whether the car is in contact. So the answer is no. Full stop. It's not in contact because the centripetal acceleration is less than 9.81. That's the answer. Let's move to the next one. Suggest with reason, but without calculation, whether the conclusion in C will be different for a car of mass 460 grams with the same initial. If you remember what I did total energy at X must equal to total energy at Y. At the end of the day, potential at X is 0. Kinetic at X, we have half m 3.8 squared. Total energy at Y, potential at Y, I think we have mg 0.62, and kinetic at Y, I think we have half m vy squared. Now the question asks us that they ask us to suggest with reason, but without calculation, whether your conclusion in C will be different for a car of mass 160 grams. Now, they've increased the mass. Doing my calculation, I divide through by mass. At the end of the day, I have this. I divide through by mass. At the end of the day, I have this. What do you notice? At the end of the day, I have this. What do you notice? So in concluding about that, mass has cancelled out. So mass has no impact in determining whatever I want to determine in C, which means that since mass cancels out, so I just need to write mass cancels out in the equation above. So it makes no difference, or is independent of the equation. That's the answer. The next example. Okay, the next question is a large bowl is made from part of a hollow sphere. A small spherical ball is placed inside the bowl. Okay, there's a small spherical ball in the bowl. You can see it where it's moving in circular path. You can see it moving in circular path with a horizontal speed. The ball follows a horizontal circular path, constant radius. You can see the radius. The radius is 14 centimeter, which will be 0.4 meter when divided by 100. So, which will be 0.14 centimeter. So, the forces acting on the ball are weight, normal reaction. Normal reaction, weight is W in this case. Normal reaction force is R of the ball, as shown. You can see by resolving the normal reaction, it at an angle theta. Okay, whenever you see that, they want us to resolve. The normal reaction, y and x. Let's get y. Sine theta is y over r. Everything go to normal reaction. When you resolve normal reaction vertically, so this place is r sine theta, which is always, the vertical force is always equal to the weight. X, let's get x, adjacent over hypotenuse. So x is r cos theta. So this one here is the one that always provides the centripetal force. So, and by resolving the two perpendicular components, show that the resultant force F is given as the expression. Now, r sine theta, the vertical force r sine theta is always equal to downward force after resolving. So r sine theta is equal to weight, equation 1, and r cos theta is always equal to centripetal force F. So from here, so equation 2, now since we are asked to find W equal to F tan theta. Okay, to get tan, the only way is tan is sine over cos. So to get sine over cos, let's divide equation 1 by equation 2. Oh, there's a space for it here. Equation 1 divided by equation 2. R sine theta over R cos theta, W divided by F, centripetal force. R cancel out. Sine over cos is tan theta equal to W over F. Cos multiply, so W equal to F tan theta. That is what they are asked us to prove. F tan theta. Now the next question. State the significance of force F. Okay, force F provides the centripetal force. I said it earlier. Provide the centripetal force. Now, the next question. The ball moves in a circular path of radius 14 centimeters. For this radius, the angle theta is 28. Calculate the speed of the ball. Okay, calculate the speed of the ball. The expression given to us earlier, the expression is W equal to F tan theta. There is always a reason for previous question in CAIE question. W is mg, that's weight. F is centripetal force. Centripetal force. Okay, speed. Yeah, which can be mv squared over r, not angular speed. Mention speed, so that's okay. Tan theta. Mass cancel mass. So from here, I can have rg and I cross multiply v squared tan theta. So v squared is rg over tan theta. So v is square root of rg over tan theta. So I can get the speed now as what's my radius? 0.14 g 9.81 over tan theta, that's tan 28. So punch that into your calculator. So when you punch that into a calculator, so you're going to have 2.58. The square root to give us 1.6 meter per second. That's it. Okay, that's it. So the next one is this question. Okay. We have to define radian. We are asked to define radian. How do we define radian? We have to define the radian. Let me change my color for this. Now, how do you define radian? If you are following my series, I just started in for A2. Okay. For an object in circular path, let's say this object in circular path is here. The object has changed direction, is now here. It's been displaced from A to B. Initially, it's been displaced. This is the radius. So it's been displaced. So this theta is displaced in an angular form, not linear. So now this theta at the middle is called angular displacement. It's called angular displacement. An angular displacement is measured in radian, and they are now asking us to find the radian. Now, at the same time, we have a relationship. Length of an arc, it been displaced in this curved path. Length of arc is r theta. So theta can be this over r. Theta can be length of arc over r. If you are asked to define radian, now theta is measured in radian. So to get 1 radian, which means that the length of the arc must be 1 and the radius must be 1. 1 over 1 will now give us 1 radian. So we can use this concept to define the radian. So the radian is defined as the angle. First of all, tell them where you can see it, as the angle subtended at the center of the circle by an arc equal of length to the radius, equal of length to the radius of the circle, equal of length to the radius of the circle. The angle subtended by an arc, subtended at the center of the circle by an arc equal of length to the radius of the circle. Yeah. So with this simple logic, so for us to get radian, the length and the arc, the length of arc and the radius must be equal. That's it. Let's move to the next one. Explain what is meant by angular speed about point P of mass. Angular speed, the symbol is W, angular speed. So we have to explain angular speed about point P of the mass. Angular speed, as you all know, is angular displacement over time, but it's the specified angular speed about the point P of the mass. So the mass is this, as in when you check the question, it said a small mass is attached to a string. So it's safer to define angular speed in this case as the rate of change of angular displacement. Rate of change of angular displacement. Rate of change of angular displacement of the spring or by the string. Rate of change of angular displacement by the string. So it's safer to do that. So rate of change of angular displacement by the string. Okay. The next question. We have horizontal flat plate is free to rotate about the vertical axis through its center as shown. A small mass m is placed at a distance d. Look at the small mass. It's placed at a distance d from the axis of rotation, the center. The speed of rotation of the plate is gradually increased. The speed of rotation is gradually increased from 0 until the mass seen slide off the plate. They are increasing the speed gradually until the mass you are looking at slide off this plate. The maximum frictional force between the plate and the mass. This is the frictional force between the plate and the mass. W is the weight of the mass m. The distance d is 35 centimeters. Determine the maximum 5 max. Determine the maximum number of revolution. Determine the maximum number of revolution of the plate per minute. It has to be per minute for mass M to remain on the plate. Now, we are given that the frictional force is 0.72 weight. In this case, the frictional force is equal to 0.72 weight. And the maximum, from this place, the maximum frictional force between the plate and the mass is given this expression, between the plate and the mass, which means the frictional force is the one keeping the mass on the plate. So which means the frictional force is the one that provides, in this case, frictional force provides centripetal force. The fact that they keep the plate, the mass on the plate, is the frictional force that provides centripetal force. And centripetal force can be mv square mrw square. Why I'm using w square is because the question asks us to determine the number of revolution. I know it has to do with angular speed, equal to 0.72. What's the weight? Weight is mg. Mass cancel mass in this case. So from here, I have w square equal to 0.72 g. G is 9.81 all over radius. What's the radius of the question? They gave us the distance between the center of rotation and the mass is 35 centimeters. That's the radius. Take it to meter, 0.35. So in this case, angular speed with square root of 0.72 multiplied by 9.81 divided by 0.35 will give us the angular speed. So in this case, the angular speed is 4.49. Angular speed is measured in radian per second. Is measured in radian per second. But the question asks us to find it evolution, the number of revolution per minute. Okay, it has to be in per minute. So let's look at it like this. Remember that 1 minute is 60 seconds, or 60 seconds make 1 minute. So if 1 minute is 60 seconds, we can also do like this. 1 minute is 60 seconds. That's 60 times 1 second. Now, behave as if you are making 1 second the subject of formula. So 1 second will be 1 minute over 60. So if 1 second is 1 minute over 60, then I'm going to have this. I'm going to have this. But at the end of the day, the question wants us to leave it in per minute. Oh, revolution per minute. Revolution per minute. Already we have radian per second. So these radians must turn to revolution. Seconds must turn to minutes. Now I have seconds. 1 second is 1 minute over 60. I've made second the subject of formula. Let me find a way to do for revolution. You know, 1 revolution, of course, you know, is 360 degrees. And 1 revolution, 360 is 2 pi radian. Of course, you agree with me, which is the same thing as 2 pi times 1 radian. So behave as if you want to make 1 radian the subject of the formula. That will be 1 revolution over 2 pi. So 1 radian means, in terms of evolution, 1 radian means 1 revolution over 2 pi. In terms of minutes, 1 second is 1 minute over 60. This is what I need to convert it. So let's go back. So we have 4.49. Remember, radian is on top. And what's our radian? Our radian is 1 revolution over 2 pi. Remember, that's radian divided by second. 1 second is what? 1 minute over 60. So therefore we have this. So 4.49 divided by 24. So that gives us 0.1871 revolution divided by 1 divided by 60. That gives us 0.0167. No, there's minutes there. So the angular frequency or angular speed will now be 0.1871 divide 0.0167. So that gives us let me confirm it properly. Oh, this is 2 pi, not 24, sorry. So one revolution is one radian is one revolution about 2 pi, sorry. This is 2 pi. This is 2 pi. So this will be wrong. So to be 4.49 over 2 pi. So angular frequency or speed in terms of that 4.49 4.49 divided by 2 pi. I think I have 0.7146. 1 divided by 60. I think I have 0.0167. Let's divide it. 0.7146 divide 0.0167. So it gives me 42.79. So remember, to which is 42.79, that's 43 revolution per minute. That's it. Now, the last part of this, the plate in B is covered when stationary. When it's stationary, it's covered. When stationary, it's covered with mud. Suggest and explain whether the mud near the edge of the plate or near the center will first leave the plate as the angular speed of the plate is slowly increased. You know, centripetal force can be mv squared over r. Centripetal force can also be mlw squared. In this case, irrespective, v is still lw. So everything still boils back to this. So let's make use of this relationship. Now, remember that the question says state and explain whether the mud near the edge of the plate or near the center will first leave as the angular speed is slowly increased. Let's check what is happening. The question says the speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off. Now, when the angular speed increases, so in this case, as the angular speed increases, centripetal force increases, so the radius also increases. So if this is what is happening, as the angular speed is slowly increased, the centripetal force increases, as centripetal force increases with radius. So the mud flies off. The mud flies off first. at the edge. That's it. The mod keep creating distance from the center. As the angular speed increases, keep creating distance because centripetal force increases, so it flies off. Okay, the next question. We've defined this earlier, so it's same as above. Second question. Why one complete revolution is equivalent to angular displacement of 2 pi radian? Okay. Remember that length of an arc is r theta. One complete revolution is equivalent to 2 pi. Okay. Is equivalent to angular displacement. So angular displacement is theta. So let's make theta the subject of the formula. Theta is s over r. Now, for one complete revolution, the distance covered is 2 pi r divided by radius. Radius cancel radius. So theta equal to 2 pi radian. Simple. This is what they asked us. Now the next question. An elastic cord has an unextended length of 13 centimeters. The original length is 13 centimeters. That's the original length. So one end of the cord is attached to a fixed point C. One end of the cord is attached to a fixed point C. Okay. A small mass of weight 5 Newton is hung from the free end of the cord. A small mass of one end of the cord is attached to a fixed point. Remember the original length is 13, but this is 14.8, which means it's been extended. There's an increase from 13 to 14.8 by the application of 5 Newton weight. So there's a weight attached. So because they said one end of the cord is attached to a fixed point C. This is a fixed point C. A small mass of weight 5 Newton is hung from the free end. Look at it, they said mass. So it's the mass that was hung here, 5 Newton, that definitely caused this increase in length. So in this place here, the extension is a new length, 14.8 minus original length, 13. So in this case, extension is 14.8 minus 13. So extension is 1.8. Take note of the unit, 1.8 centimeter. Yeah, Hooke's law. So what is holding this mass is a rope, tension. So if you obey Hooke's law, tension will equal to kx. So let's find the first constant of this rope anyway. First constant of this spring, provided they are using the same spring, the first constant is the same thing, is tension. So in this case, when you hung the mass, it extended. So the tension and the weight are the same. So the tension is 5, while the extension is 1.8. So 5 divided by 1.8, we have 2.8. So the first constant is 2.8 Newton per centimeter. That's it. The tension here is equal to the weight. Once the mass is displaced downward, so it can only displace up to the strength of the tension. At the point it stops, the tension is equal to that weight at that point. So that's why I use 5 Newton. Now the cord and mass is now made to rotate. Like, okay, it's even clearer. At this point, they are not rotating. So now they are made to rotate at a constant angular speed W in a vertical plane about point C. When the chord is vertical and above C. When the chord is vertical and above C, the length is unextended and the length is 13 centimeters as shown. Now this is C, is now above C. Is above C here. They said the length is unextended, which means at that particular moment, this is the original length. The length is unextended. The fact that it's unextended, extension only takes place when there is force, which means there is no force here because the length is not extended. Now the mass is here above C, so which means that the weight of the mass will act downward, mg. So in this case, the weight of the mass in this case, the weight of the mass is what is providing centripetal force. Centripetal force in this case, because it's only the weight that made the mass downward, no tension in this case. The first question show that I'm coming to this diagram, they did not mention anything about this figure 1.3. Show that the angular speed of the chord and mass is 8.7 radian. So since centripetal force would provide the weight, centripetal force is mRw squared. The weight is mg. I'm looking for angular speed w. So mass cancel mass. W squared equal to g over radius. So in this case, angular speed is square root of g over the radius. So angular speed is measured in radian per second. So take note. So the g is 9.81 in meter per second square. The radius must also be in normal unit. The radius in here should be 13. Do you know why? Because this is an unextended length, and distance from the arc to center, the center is C. The distance from the arc to center is radius, and so the radius in this case is 13 centimeters. Since all the units are intact here, so the length should be 0.13. So let's find 9.81 divided by 0.13. So it's going to give us 8.7, 8.6 something, so 8.7 radian per second. So this is it. Now the next question, the chord and the mass rotate. Now the chord and the mass rotate. Remember the question said they rotate to be at this point. Now the question said the chord and the mass rotate so that the chord is vertically below C. Initially it was above C. Now it's vertically below C as shown in the third diagram. Look at the third diagram. It's vertically below C. In this case, the weight will act downward. Tension, there will be tension that will stretch up. So in this case, resultant force, is a circular motion. Resultant force in this case will be tension minus weight. And resultant force is always centripetal force, which is tension minus weight. So the question asks us that we should calculate the length of the chord, assuming Hooke's law is obeyed, the length of the chord. From the analysis earlier, resultant force is tension minus weight. Remember, we have to find the length in this case. Is in centimeter. Resultant force is centripetal force. Centripetal force is mRw squared equal to tension minus weight. So mRw squared. Assuming Hooke's law is obeyed, tension is kx. So minus weight. Weight is mg. Now let's analyze it. What's the mass? The mass, we are given weight to be 5 Newton. So mg is 5 Newton. So mass is 5 over 9.81. So the mass will be 5 divided by 9.81. So our mass will be 0.5097. The mass is 0.5097 multiplied by radius. So what's the radius of the circle? The original length, that's 0.13. Angular speed 8.7 all square. Remember we have so the centripetal, this is centripetal force anyway. The first constant, we got it earlier. The first constant is, since the length is centimeter, don't convert anything here. So the first constant is, I think we got it before, 2.8 something. 2.8 Newton per centimeter. 2.8. X is extension. Extension is new length. There's a new length when it's vertically below C. There's a new length when vertically below C. So minus original length. Original length is 13. I'm not converting it. So minus mg is the weight. The weight is 5 Newton. So we need to be very careful with the conversion. Let's look at it like this. We need to be careful with the conversion. Let's interpret it again. So from here, what's the mass? Okay, the mass is 5 over 9.81. Here, we are giving weight as 5 Newton. So that will give us 0.5097. What's the radius? You are dealing with this diagram C. So the radius is from arc to the center. That's L. We are not given. So the radius is L. The angular frequency or speed, we've put it before, that's 8.7 square equal K. K is Hooke's law. K is Hooke's law. Let's convert everything properly. For me, our K is 5.5 divided by 1.8. This is centimeter. Let me take it to meter. So my K will be 277 Newton per meter. Let me convert it. So my K is 277 Newton per meter. So let's put it there. K is 277. X is extension. Extension is new length. The new length is L in this question. This is a new length, L, minus original length. Original length is 13 centimeter. The original length is the one without force, which is 13 centimeter. To meter is 0.13. 0.13 minus mg, that's the weight, 5. So from here, when you multiply this times this, punch your calculator, that will be 38.57 38.5792 L equal to, open the bracket, here we have 277, that's 278, and you approximate 278 L minus 278 times 0.13, that gives us 36.14 minus 5. Collect the like stem, this one comes here. So what do you have? So when down comes there, we have when you subtract 38.579 minus 278, we have minus 239.42 L equal to, this one will give us minus 41.14. So minus, cancel minus, divide both sides by 239.42, 239.42. So L will give us 0.1718. This is a meter. So take it back to centimeter the way the question wanted, times 100. We're going to have 17.2 centimeter. So L is 17. This is the end of circular motion work example. Feel free to send me an email, ask questions. See you in the next class, gravitational field.